Hi, I'm Srinadh from UT Austin. I'm presenting here my work on low rank approximation today. The problem here is simple. Given a matrix, you want to compute low rank approximation of the matrix. And often the sizes of the matrix are large, n by n matrix has order n square entries, which can be huge for a large n. And just accessing such a matrix from the hard disk takes huge amount of time. And there is an interest in designing algorithms that access data only once or twice. So here we present one such algorithm. What our algorithm does is it takes the matrix which has order n square entries, and it forms a sketch of the matrix which is only of a size linear in n. And the way we form the sketch is by sampling a few entries of the matrix, and the sampling distribution is based on just the row norms and column norms of the matrix. So in one pass of the data, we can compute the sampling distribution, and in the other pass of the data, we can compute the samples. And once we have these samples, we use only these samples to factorize, compute the factors of the matrix. The way we do it is as follows. We do what is called as weighted matrix completion here. We minimize the error over the sampled entries, which is weighed by the sampling probabilities. And the way we minimize is through this method called alternating least squares, where we fix this matrix n by r matrix U and solve for the matrix V. And similarly, we fix the matrix V and solve for the matrix U. And note that these problems are just simple least squares problems, and you can solve them very efficiently. And once we do order log 1 over epsilon such iterations, what we can show is the error in spectral norm to the true matrix is bounded by the best rankr error you can achieve by doing SVD, plus a epsilon approximation error obtained by doing this approximation algorithm. And the number of samples you need for getting such approximation is only order nr cubed by epsilon square. So this is our main result, where we show that just sampling linear number of entries will give you an epsilon approximation to the best SVD possible. And further in simulations, we see that our algorithm compared with standard random projections or sparse embedding achieves a good error rate as we increase the amount of noise. And finally, we also compare here with running times and error rates of standard algorithms like random projection, Hadamard transform, or sparse embedding. And we show that our algorithm achieves best of both worlds, where the computation time is depends only on input sparsity of the matrix, and the error rates are the best possible in spectral norm. And further, we show application of this idea to different settings. First such setting we consider is basically a case where we want approximation of product of two matrices A and B. And computing such a product itself is a very costly operation. So what we suggest is basically sample few entries from the product using this distribution, simple distribution, which depends on the row and column norms of A and B. And we compute only those entries from the product. And this is again like you need to compute only linear number of entries from the product, and it takes a few amount of time. And once we have that sampled entries, we compute the factors again using this weighted alternating least squares method. And we can show that the error rate you can achieve is again similar to as if you have the entire matrix. So this way we can save on computation by not actually computing the product. And the other case of interest is basically the distributed setting, where one has the matrix that is distributed across S servers in a row partition model, where different rows of the matrix are at different servers. And the goal is again to compute a rankr approximation, but with low communication complexity, because in such distributed systems, the communication complexity becomes a huge bottleneck. And what we show here is that using this kind of sketching plus low rank alternating least squares ideas, you can compute such a distributed PC in such a distributed setting with very small communication complexity. In fact, we show that our algorithm has a computational complexity that depends only on like leading term of ns, and is good for like for square matrices. Our algorithm has at least as good complexity as the existing algorithms, or is sometimes better. And so these are the various applications of our low rank approximation algorithm. Thanks.